In our last class, we were seeing we completed our fan of flow in our third module, and we have started with our Rayleigh flow in our last class. We have seen one problem also in Rayleigh flow. So we will continue with the Rayleigh flow problems. So for our cat one, we will have the portions up to fan of flow. That is whatever we have seen in our last class. So for those portions, I have uploaded in our LMS those material. So please prepare. Okay. So this part will not be covered in the cat one. So 2.5 units. First 2.5 units will be for our cat. Okay. So let me go to the next problem on Rayleigh flow. We all know that Rayleigh flow is nothing but flow in a constant area duct with heat transfer without friction. The flow taking place in the combustion chamber heat exchanger are considered to be the Rayleigh flow models. So we'll have to use Rayleigh flow tables in our gas tables for solving such problems. So we have seen the theory part in the previous class itself. So we will see the problems on this Rayleigh flow now. One problem also we have seen in our last class. Second problem we'll see. The Mach number at the exit of a combustion chamber is 0.9. The ratio of stagnation temperature at the exit and the entry is 3.74. The pressure and temperature of the gas at the exit are 2.5 bar and 1000 degrees Celsius. So we need to calculate the Mach number, pressure and temperature at the inlet, heat supplied per kg of the gas, maximum heat that can be supplied. So whenever the word heat comes, it is only for Rayleigh flow, because we can just compare it. We have seen the comparison in the last class. Let us just see that. Comparison of all the three types of flow, whatever we have seen. This is the comparison: isentropic, Fano, and Rayleigh. So in this Rayleigh flow, heat transfer is considered, no friction is considered. In no other flows, heat transfer is considered, isentropic and Fano. So whenever the heat transfer word comes, so it is completely Rayleigh flow. And then stagnation temperature is only varying in the Rayleigh flow. No other flow, the stagnation temperature is varying. So they are given the stagnation temperature ratio is given. It is other than 1, right? 3.74. So it is only a Rayleigh flow. So like that, for some of the keywords will indicate the type of flow here. In no problem, they will specify the type of flow, as we discussed already. Yes. Now let us proceed with this problem now. We'll take gamma as 1.4 and 1.1 kilojoules per kg Kelvin. This is given in the problem. So if you see it, M2 is given and T02 by T01 is given. T02 by T01 ratio is 3.74 and the exit pressure and the temperatures are given 2.5 bar and 1000 degrees Celsius. So we'll convert in Kelvin. So since Cp is other than 1.005, we need to calculate it. If gamma is 1.4 and Cp is 1005 means we can take R is 287. So here we need to calculate the R value. For that we can use this relation Cp equal to gamma by gamma minus 1 into R, which we have already derived in our first module. By using this we can able to get our R value here. If nothing is specified, you can simply take R as 287. Okay. Now we'll proceed with the problem to find out the required parameters. Initially, we need to find out the Mach number, pressure, and temperature at the entry. So we are going to use our gas tables. So let us go to our gas tables and we'll use it. We'll take the contents page. So here we have a Rayleigh flow is there. Rayleigh flow of perfect gas heat transfer, Rayleigh flow in this gamma equal to 1.4. So let us take page number 111. So we have M2 is 0.99. So let us take these ratios: pressure ratio, temperature ratio, and the stagnation temperature ratios. Let us take these three parameters now. M2 is 0.9. So M2 is 0.9 here. So for this, we'll take P2 by P star as 1.125. P2 by P star is 1.125, and you'll have T2 by T star. So T2 by T star is 1.025, 1.025 T2 by T star, and the stagnation temperature ratio T0 by T0 star. So that is 0.992. So 0.992 we have taken. So already we have seen this is nothing but P2 by P2 star and T2 by T2 star. Similarly, this is T02 by T0 star. There is no need of putting 2 here because critical properties are only at one state only, m equal to 1. So there is no need of putting 2 here, even if you put nothing wrong in that. So we'll get the critical properties now from this. So we'll calculate P star and T star, substituting the values of P2 and T2 because those values are with us. P2 is 2.5, so that we'll get P star as 2.22 bar when you substitute in this expression. So substituting the T2 value as 1273, we'll get our T star as 1241.95 here. Okay. So now also we have seen that for our Rayleigh flow and Fano flow, we can use gas tables. We can use isentropic table. So that also, this isentropic flow table can be used to obtain T by T naught and P by P naught for Fano flow and Rayleigh flow problems. So for taking only these two ratios, we can use isentropic flow tables for Fano and Rayleigh flow problems. So that we need to remember, because this is an adiabatic energy. This has been obtained from adiabatic energy equation. This equation is applicable for all these flows. The reason is they don't want to repeat again in the Rayleigh and Fano flow table. That's why we are referring isentropic table. Now corresponding to this M2 0.9, we can take P by T naught and P by P naught. So let us go back to our isentropic table and take isentropic table. Isentropic table, page number. It is 28, correct, for gamma 1.4. So let us take page number 28 here. We need M2 is 0.9. So for M2 is 0.9. First one is T by, second and third column we can take 0.9. 0.861 is T by T naught and this is P by P naught. So 0.861 and 0.591 T by T naught and P by P naught. So T2 by T naught is 0.861 and P2 by P naught is 0.591. So knowing T2 and P2, what we can do, we can able to calculate our T02 and P02. Okay. So if you see it here, we can T2 is given, T2 is 1273. So T02 we can get it as 1478.5. And here also we know P2, so we can write P02 equal to P2 by 0.591. P2 is 2.5, so we'll get our P02 as 4.231. So what we can do it now, we can also have this ratio here. Where is that T02 by T01 ratio? Okay. So if you see here, T02 by T02 ratio. 1 minute. We need to use this ratio. For this, we need T02. Stagnation temperature. Only they given the ratio. Okay, so we need to get our T0 as star. Okay. Yes. Okay. So we are going to use this ratio T02 by T01. We have calculated this T02 here, so that by using that ratio we can able to get T01. So in that way only we have proceeded this problem. So we have calculated T02 1478.5. By using that ratio of T02 by T01 3.74, we have substituted. T02 1478.5, we got T01 as 395.32. Okay, and then this one, if you see it here, after getting our T02 here, you see here after getting this T02 here, we'll substitute this T02 here, we got T0 star. We know T02 we have substituted here, so we got T0 star here. So what we'll do now, we'll form a ratio called T01 by T0 star, because we know T01. The reason is we need to get inlet properties now. So that is the parameters we need to find as per the problem. So that means any one of the inlet parameters we are trying to get it from the gas tables. So for that, the possibility is we have T naught star and we know T naught one. So I'm writing this ratio so that corresponding to that I can get the rest of the values from the Rayleigh flow table. So we'll form T naught one by T naught one star ratio. So that value will substitute 395.31 and T naught star is 1490.42. So we'll get this T naught 1 by T naught 1 star is 0.2652. So for this, we'll refer our isentropic Rayleigh flow table. We need to have 0.26. So T naught 1 by T naught star should be 0.26. So I'm going to see here. So 0.26, if you see it here, so this may be between 0.239 to 0.274. So you can take the average of this one. 0.26 we need, or you can just take 0.26, that is also correct. The answer will not vary much. Either you can take average of these two, otherwise you can take this as 0.26. Okay, so if you see it here, corresponding to this, we have taken this M1 as 0.26, this one. Okay, for the T naught 2 by T naught 1 by T naught 1 star ratio, and we have taken T by T star and P by P star also. So this is your second and third one. P by P star is 2.193 and this one is 0.325. So 2.193, 0.325. So once we got this, already we know these critical properties T star and P star. We have got it already. So that we have calculated T star and P star values. This is 1241.95 and 2.22 bar. So that we can get our T1 and P1, which is the required inlet properties in combined with M1 also. These three, the first parameter we need to find. Next, they are asking us to find out the heat supplied per kg of gas. So in our while you are seeing the theory part of Rayleigh flow, we have seen that heat supplied can be written it as Q equal to mCp into T02 minus T01. If there is unit mass, we can write Cp equal to T02 by T01. So we know these two values. T02 is 1478.5 and T01 is 395.52. So we'll get our Q as 1191.5 kilojoules per kg. So this is the heat supplied per kg. Next, we can also find out we have been asked to find out the maximum heat supply. So how do you get maximum heat supplied? When there is a limiting state for maximum heat supply. We have seen it. We have, if you see our previous class notes. So this is the state where we have the maximum heat supply. T naught max or T naught star, which is equal to M equal to 1 here. So there is a limiting state in this Rayleigh flow where we can supply that means the supplying of heat is limited in the case of a Rayleigh flow. We cannot keep on supply the heat to the in the case of a Rayleigh flow, because here we have the limiting state here. If it exceeds, it means the decrease in entropy. So that is not possible. That's why we got this limiting state. So accordingly, so T naught star, whenever I'm using this T naught star, this is the maximum stagnation temperature. So for that only, we can, for if you want Q max, we'll use this T naught star here. So instead of T naught 2, we can substitute T naught star here. So it is mCp into T naught star minus T naught 1. T naught star also we have calculated. So that is 1490.42 and T naught 1 is 395.32. So we'll get our Q max as 1204.6 kilojoules per kg. So I hope you understood this problem. Okay, we'll go to the next problem. Uh, Air at 1.5 bar and 30 degrees Celsius enters a constant area pipe of 5 centimeter diameter with a velocity of 35 meters per second. So we need to calculate the maximum heat that can be added, and we have been asked to calculate the exit condition if the 50% of the maximum heat was added. So we need to calculate the Q max, and if Q equal to 50% of the Q max, then what are all the exit conditions? So in this way, we have to proceed with the problem. And once if the term heat comes, it is only a Rayleigh flow. Fano and isentropic flow, we don't have any heat transfer part. So it is a Rayleigh flow problem, constant area pipe. So the given data is inlet pressure and temperatures are 1.5 bar and 30 degrees Celsius. Pipe diameter is 5 centimeter. So velocity is also given, which is 35 into 10 power minus 2, 35 meters per second. Yes. So let us first find out the Qmax here. So if you see here, we have the limited data. We cannot directly use the gas tables here. So let us try to find out the Mach number and then we'll proceed with this. So Mach number, the very basic relation, M equal to C by A, we'll use it. Since P1 and T1 is given, I can write it for the inlet condition. M1 equal to C1 by A1, A1 equal to root of gamma R T1. So gamma will take 1.4 and R is 287 and T1 is 303 Kelvin. So we'll get our A1 as 348.92. Substituting A1 here, we'll get M1 as 0.1 here. Okay. Now we'll write this relation Qmax equal to, so we'll use it later, this Qmax equal to mCp into T naught star minus T naught 1 here. See, in the previous we are finding per unit mass, here they given the velocity here. So velocity means we need to consider a mass flow rate. This is a fluid. So that we need to get our mass flow rate here. So mass flow rate can be written as rho AC. So we can find it for the inlet condition, rho 1 A1 equal to C1 here. Rho 1 can be calculated by writing the relation P1 by R into T1 here. So P1 is 1.5, we have to write it in Newton per meter square. So 1.5 into 10 power 5, R is 287 and T1 is 333. T1 is 35 meters per second. It is a circular pipe, so it is a cross-sectional area is 5 by 4 d square. So we'll substitute these values and we'll get mass flow rate as 0.1185 kg per second. And still we need T01 as well as T0 star here. So let us refer our isentropic table to get our T01 here, because stagnation temperature ratio is available only in the isentropic table. So what we'll do, we'll take our isentropic table, which is at page number 38, and that is 28. So here we'll take our M1 as 0.1. For 0.1, we'll get our T by T0. So second, this third column is T by T0, 0.1 equal to 0.998. So point T1 by T0 is 0.998. T1 we know, so that we will get our T01. T01 as, so by writing the ratio of T1 by 0.998, it is 303 by 0.998. We'll get T01 as 303.6. So this T0 star we need, this is available only in the Rayleigh flow, T0 star. So for the same Mach number, we'll refer our Rayleigh flow now to get the temperature as well as the pressure ratios as well as stagnation temperature ratios. Okay. So for this, I am going to refer our Rayleigh flow table, which is at 111. For the same point 1 here, which is at the fifth column. Point 1 is T0 by T0 star is 0.0468. 0.0468. So let us take this 0.0468 here. Already we know T01. So we can write T naught star equal to T naught 1 by 0.0468. Substituting the T naught 1 values, we'll get our T naught star as 6487.336. So we have all the values to calculate the Q max here. So m dot we know, Cp also we know, T naught star minus T naught 1. So m dot 0.1185 and Cp is 1005. T naught star we have got as 6487 and T naught 1 is 303. So we'll substitute this, we'll get our Q max as 736.435 into 10 power 3 joules. So we are writing in kilojoules here. So it is given that actual heat transfer is 50% of the maximum possible heat transfer. So we'll get our Q as 0.5 into Q max. So Q we obtained as 368.217 kilojoules. So what we'll do it here, we have been asked to find out the exit conditions, all the exit properties we need to find out. So let us try to get any one of the exit parameters ratio, and then we'll take the rest of the values from the gas tables. So we are going to get our T naught 2 from this expression. Since we know Q, we can write this expression Q equal to m dot into Cp T naught 2 minus T naught 1. Q is 368.21 and m dot is 0.1185, Cp is 1005. T naught 1 we know, and T naught 2 we need to find out here. So that we got our T naught 2 as 3395. So here, since we substitute in joules per kg Kelvin, here it should be in joules. So we have to multiply with 10 power 3 here. If this is kilojoules means we can put 1.005. So we have to be careful. We'll tally with the units. This is joules means this should be in joules per kg Kelvin. So we'll get our T naught 2 as 3395.47. So now we can form the ratio as T naught 2 by T naught star, because already we know T naught star here. So T naught 2 is 3395.47, T naught star is 6487, and we'll get our T naught 2 by T naught star as 0.5234. So this value we'll get from our Rayleigh flow table. Corresponding to this value, we'll get the rest of the values. We have got the one of the exit properties. T naught 2 by T naught star as 0.5234. Let us take 0.52. So let us take this 0.52 here. If you want accurate interpolation, you can take the average of this. So here we will take 0.4. Here we will take 0.4, which is 0.52. For 0.529, we have 0.4 here. So we'll take M2 as 0.4 here. Let us take rest of the ratios also. So let us take this T naught P star and T star. So first one and second one and fourth one. So second one is, this is 1.961. We have 1.961 as P by P star, and T by T star is 0.61. Where is it? 0.615. Yes. So here we have 0.615. So the critical properties already we know. So we'll write T2 as 0.615 into T star. So we'll get our T2 as 3327.58. And P2 by P star ratio, we can write P2 equal to 1.961 into P star. We'll get P2 as 1.24 bar. Okay. And we have been asked to calculate all these parameters. So we have successfully calculated. Okay. Exit properties and then your Q max. These are all the parameters we need in this problem. Maximum heat, exit conditions, the 50% the maximum heat was added. That's all. So in Rayleigh flow, they may ask in different kind. If you are confident of using gas tables, then there won't be any problem. You can easily solve it. The next problem. What is the value of Mach number of air at maximum enthalpy point in Rayleigh heating process if the conditions at the sonic points are P star equal to 1.6 bar and T star equal to 500 Kelvin? Calculate the pressure, temperature and velocity at maximum enthalpy point. What is the change of entropy between these points? So here it is given that maximum enthalpy point in Rayleigh heating process. They are asking what is the Mach number at the maximum enthalpy point in the Rayleigh heating process, and they are given it as at m equal to 1, P is 1.6 and T is 500. That is that itself P star and T star. And at this maximum enthalpy point, they are asking us to find out the temperature and velocity and also the change in entropy. So in our theory part, we have seen that there are three limiting states. One is for the entire flow process m equal to 1. Another one is for the increase in heat transfer, that is the stagnation temperature. Another one is the increase in static temperature. This diagram you can understand. This point E refers the limiting state for the increase in static temperature. So that has been found as m equal to 1 by root gamma. So that means if I am substituting the gamma, given gamma value here, I'll get that Mach number there. So at that point, they are asking us to calculate the pressure. They are asking us to calculate the temperature, velocity, and pressure. So in the point E11, they are asking us to calculate this temperature, velocity, and also the pressure. So first, if you substitute the m equal to 1 by root gamma, gamma is 1.4, so you will get our Mach number at point E is this point, 0.845. So for this 0.845, now we'll refer our Rayleigh flow table. For gamma is 1.4. 0.845. Okay. So 0.845 is nothing but 0.85. Either you can take average of this or you can take 86, no problem. 84, 85, any of these two values you can use it. So you'll get the same answer. There won't be much variation in the answer. So if you see it here, so we used 0.84 as 1.027. So that is our P by P star. So P by P star is 1.207. So since we are saying it for ME, we can write it as PE. PE by, this is PE star or simply P star. And T by T star is 1.028, is 1.028 here. So P star and T star is given in the problem, which is 1.6 bar and 500 Kelvin respectively. We'll get our P by writing 1.207 into P star 1.93 bar and T equal to 1.028 into our T star, which is 500 Kelvin. So we'll get our T as 514. So we can also find out the velocity by writing m equal to C by A. So C equal to m into A here. When A equal to root of gamma T, A can be written it as root of gamma T. So m is 0.845 and gamma is 1.4 or 287 and T is 514. We have calculated just now. So we'll get our C as 384 meters per second, which is the velocity at this maximum enthalpy point. We've been also asked to calculate the change in entropy. So from a thermodynamic relation, we can write the change in entropy in terms of temperature, pressure, and also temperature and volume. Also, we can write it. So that basic relations we have specified it here. S2 minus S1 equal to Cp into ln of T2 by T1 minus of R into ln of P2 by P1 here. Okay. So the same thing that we can write it as according to this our gas dynamics problem. So this is the initial state and this will be the final state. Always the star will be the final state. So this one can be written it as the what is that maximum enthalpy point E and 2 will be the final state here. So accordingly here also we'll change it. 2 will be replaced with hash and 1 will be replaced with E here. So in this way we can write S star by S equal to Cp into ln of T star by T minus R into ln of P star by T here. So that relation we will substitute it here. So already we know T by T star and P by P star. In all our gas dynamic problem, that ratio is easily used. The ratio can be easily used. So this ratio I can write it here. So since it is T star by T, I can write inverse of this one. So this will be 1 by 1.028. This will be 1 by 1.27 here. So that you will get our change in entropy here. Okay, that is minus 27.5 plus 53.87 will give the this this addition. So we'll give the final answer of entropy LS. Okay. So maximum enthalpy point means, so we need to remember that is m equal to 1 by root gamma. It is the another limiting state for the increase in static temperature or static enthalpy. Okay. Next, there's another problem. Uh, air at a pressure of, ഇതിൽ ഏതാ doubt irukama? Any doubt please? All the gas dynamics problems are similar way of proceeding. Only thing is we have to use the respective gas step. And I think there won't be any problem in following this. From starting from the first unit itself, we will be using the similar methodology. Using the gas tables, taking the ratio, finding the inlet and outlet properties. Yes. Next step, air at a pressure of 3 bar and temperature of 288 Kelvin and Mach number of 1.5 is brought to sonic velocity in a frictionless constant area duct through which heat transfer can occur. Since it is given that heat transfer can occur, so it will be a Rayleigh flow problem. So we have to calculate the final conditions, that is final pressure and temperature and heat supplied. So it is the initial conditions of pressure, temperature and Mach number is given. P1 3 bar, T1 288 Kelvin and Mach number M1 is 1.5 is brought to sonic velocity. That means it is allowed to pass through the limiting state. Sonic velocity means m equal to 1. So in that way we can understand it is brought to the sonic velocity means it is allowed for this till limiting state. The flow is allowed to reach still the limiting state as we are seeing it here. In the point வரைக்கும் we are allowing the flow. Even though if it is not specified, we will assume in that way only. Yes. Next, we'll use our table because we have been given the Mach numbers. Okay. M1 is 1.5 and it is brought to sonic velocity, the meaning of M2 equal to 1 here. So we'll get our M1, we'll use our M1 and M2 from the Rayleigh flow table, we'll get the respective properties. Okay, so M1 is 1.5. So from our Rayleigh flow table, M1 is 1.5 here. For M1 equal to 1.5, P by P star is 0.528. P by P star is 0.528 and T by T star is 0.578. T by T star is 0.753. 0.753. So P1 and T1 values have been given. So we can write P star equal to P1 by 0.578. So we'll get our P star as 5.19 bar. And T star can be written T1 by 0.753. T star equal to 382.5 Kelvin. In a similar manner, we can refer Rayleigh flow table for the for M2 value of 1 for the M2 value. For M2 equal to 1, we'll get the pressure and the temperature ratio. So here M2 as 1 here. Okay. So for this, obviously it is a limiting state. So it will be 1 only. P star and T star. So P2 by P star is 1.1 and T2 by T star is 1 here. So P star and T star we know, so that we can write P2 equal to P star into 1. So this is 5.1903 and T2 equal to T star into 1. This is 382.5. And we can also calculate this heat added, which we need to get in, and we'll find out per unit mass. We'll write Q equal to Cp into T02 by T01. We need both, the two unknowns are there. So for getting T01 and T02, knowing inlet conditions, static inlet conditions, we can preferably refer isentropic table. So we'll use our isentropic table. M value as 1.5. Isentropic table P by P0 and T by T0 can be used. 1.5. So for 1.5, what is the third column? So 1.5, 0.689. So 1.5 it is 0.689. And for M2 equal to 1, our T by T naught is 0.834. So we'll get as 0.834. So we know T1 and T2 here. So that we can write T01 equal to T1 by 0.689. So we'll get our T01 as 417.9. T02 can be calculated by writing T2 by 0.834. So we got T02 as 458.63. So after getting our T02 and T01, so we'll substitute in our heat transfer equation Q equal to Cp into T02 minus T01. Substituting those values, that is T02 and T01, we have calculated now. We'll get our Q as 40.846. Okay. I hope this problem also understood. Uh, it's very easy. I think we can able to understand this one. More and more problem we have seen, I think it will be easy for you to understand. Okay. So next, we'll see the final problem. The stagnation temperature of air in a combustion chamber is increased 3.5 times from the initial value. So if the stagnation temperature changes means it is definitely a Rayleigh flow. In no flow, stagnation temperature changes. And also combustion chamber is an example of Rayleigh flow model. So it is a Rayleigh flow problem. The air at the entry is 5 bar and the temperature is 105 degrees Celsius and Mach number is 0.25. You have to calculate the Mach number, pressure and temperature at exit, stagnation pressure loss and heat supplied per kg of air. So taking our given data, P1 and T1 as 5 bar and 105 degrees Celsius, will convert in Kelvin, 378 Kelvin, and M1 is 0.25. Okay. And the ratio we can get, that is T02 by T01, which is given as T02 equal to 3.5 times the T01 here. So what we'll do, first we'll use our M1. This M1 can be used for both Rayleigh flow table as well as isentropic table. So we need to have exit properties. What we are going to do, we are going to use this M1. We can take T by T0 from our T1 by T01 from our isentropic table. So we are going to find out T01 from this. So T01 we can be substituted, we'll get T02. So that T02 it is another exit parameters. With that we can get the other exit properties, and that way only we are going to do it. So for isentropic table, M1 is 0.25. So let me, M1 is 0.25. Okay, so we need a stagnation pressure ratio and also temperature ratio. Third and fourth column. 0.987 and 0.957, which are temperature and pressure ratios. So 0.987 and this is pressure is 0.95. Okay. 0.25. Point 0.987 and 0.957. Okay. So we know T1. So we can write T01 equal to T1 by 0.987. So we'll get T01 as 382.97. And also we'll get our P01, writing P1 by 0.95. So 5.22 bar. Again with the same Mach number, we can refer our Rayleigh flow table. Okay. So for Rayleigh flow table, we'll go to Rayleigh flow table. .25. So we don't have 0.24 here. Then we can take this average of this, will be better. And you can also take just 0.24 or 0.26. The value won't vary much. You can also take average. T by T star is 0.305. You see it here. This average we have taken T by T star 0.284 and 0.325. So that average we got it as 0.305. And P1 by P star, so this average we can take it 2.221 and 2.193. This average we can take it as 2.207. We know T1 and P1, so T star can be calculated by writing T1 by 0.305 and P star can be calculated by writing P1 by 2.207. So we can also get this stagnation temperature ratios T naught by T naught star for this 0.25 stagnation temperature, which is on fifth column, 0.239 and 0.274 average we will get it. So this is 0.257 we'll get, and T star we got because we know T naught 1 here, so we got the T naught star. So now what we'll do, we have been given as T naught 2 is 3.5 times the T naught 1. So T naught 1 we got it now 382.97. So the idea is we are going to form any one of the exit property ratios with available data. So it is possible to form T naught 2 by T naught star because we know T naught 2 here. So once if we know this exit, other we can get it. So this is approximately zero point 0.9. So we'll get for T naught 2 by T naught star as 0.9. We'll refer our Rayleigh flow table. Stagnation temperature is available only in the Rayleigh flow. T naught 2 by T naught star as 0.9. Okay. So either you can take this one or 0.68 or 0.7. Okay, this one, the average of this, or you can just take this one. Okay, both values are correct. So here they taken as M2 is 0.68, this one 0.893, and P2 by P star, T2 by T star. P2 by P star is we have 1.457 and T2 by T star is 0.981. So 1.457 and then 0.98. So already we have P star and T star. So already calculated. So here we have it. So that I can substitute it here. So we'll get our P2 and T2. That is our exit properties. So writing P2 equal to P star into 1.457, we'll get P2 as 3.3 bar. And T2 as T star into 0.98121.7.4. So we'll get this P2 and T2. So that because we need to calculate our exit properties. So we have been asked to calculate the stagnation pressure loss, that is del P naught. So for this we need a P naught 2. Already we calculated P naught 1 in the very first step itself. So for this we have to refer isentropic table because M2 is available with us. So we'll refer our isentropic table for getting the P by P naught. So we'll check these values. Gas tables, isentropic table 0.68. For 0.68, we have this P by P naught, P2 by P naught as 0.734. This is 0.734. So we know P2 which is 3.3. So we'll write P naught 2 as P2 by 0.734. So P naught we calculate as 4.49 bar. And stagnation pressure loss, we can write P naught 1 minus P naught 2. P naught 1 already we calculated, so that value will see it. P naught 1 is 5.2 bar, 5.22 bar. So 5.22 bar minus 4.49 bar, which will give us 0.728 bar. Heat supplied relation, we can write it Q equal to Cp into T naught 2 minus T naught 1. T naught 2 we calculated, T naught 1 also we have it. So T naught 2 has 1340.39 and T naught 1 is 382.97. We have got Q as 962.23 kilojoules per kg. Okay. In this problem, we have been given the stagnation temperature ratio and the Mach number at the entry. So we managed to find out the one of the exit properties, that is stagnation temperature ratio we obtained at the exit. With that, we have easily proceeded to calculate the all the exit properties by using our isentropic table for getting P by P naught and T by T naught. Yes. So I think you're comfortable with this problem. So let me show you. After taking the screenshot, please, this is the first problem already you've taken. Second problem, I'll just show you. You can take screenshot and see that any doubt you need it. The next problem. Okay, I will wait for some time. So please see that uh, any doubt you are having so that I can clarify. Screenshot எடுத்ததுல ஒரு go through பண்ணுங்கம்மா ஏதாவது doubt இருக்கான்னு பாருங்க. Can wait for some time. Okay, ma'am. I think I can close my presentation. If you have no other clarifications. Yes. So I'll take attendance. Kabir and Muhammad Izam ரெண்டு பேரும் கொஞ்சம் வெயிட் பண்ணுங்கம்மா கிளாஸ் அட்டெண்டன்ஸ் படிச்சுட்டு ஓகே
Okay, sir. Okay, sir.
அட்டெண்டன்ஸ் நம்ம 1012
Sir, yes, sir. Present, sir.
எஸ் and 1033
Present, sir.
Turkish. Okay.
Present.
And 1049,
Present, sir. Shakir.
Shakil. Yes. Okay. And 1050 Zama. Shakira. 1050 Shakir. And 1060.
Present, sir.
Yes. 1075 Sahiraj. Sahiraj 2016. Two thousand 2019. Arshad. Arshad India. Okay. Kabir.
Present, sir.
Syed Arshada, sir.
2019.
Sir, present, sir.
Sir, Kabir, present, sir.
Okay.
19
Adam.
present, sir.
Adam.
Adam present, sir.
Adam number என்ன?
69, sir.
69.
Yes, sir.
Okay. Exam இருக்கா? Okay.
இருக்கு சார், இருக்கு சார்.
Okay. So I have to today I'll give assignment for this cat one. I'll put it in LMS. All of you please submit. I'll give 1 week of time.
சரிங்க சார்.
Okay.
Okay, sir.
Exam and Kabir மட்டும் இருங்க மத்தவங்கலாம் can give the class.
ஓகேங்க சார்.